the free energy change for the reaction is negative. And that's right. Okay, so if you voted for D, good job. Okay. Now, 27% of you voted for E. For E, you said that whether the free energy change for the reaction is positive or negative can't be determined from this information. Okay. Now, it's true that I haven't actually told you the equation yet that relates the equilibrium constant to the change in free energy. You might have seen it already. You might know it from general chemistry, but we're going to look at that in a minute. But even if I didn't show you that yet, you should know that if we have a situation where we have more products than reactants at equilibrium, right, that this is a spontaneous reaction, and a spontaneous reaction has a negative change in free energy associated with it. Okay, so that would be the rationale for that. And a few people, 6%, voted for C, which said that the change in free energy for the reaction is positive. And you know that's not true, right, because it's a spontaneous reaction. And then just a very small number of you voted for A or B. Okay, so 60% got that one right. And if you did, great job. Yeah, question. Say again. What if you're already at equilibrium? Well, right. So if you're already at equilibrium, then the reaction, is going forward and backwards, and you sort of establish that equilibrium situation. But we're talking about here what happens in, in the case of you're starting off with a reaction who ultimately the equilibrium constant would be this. Make sense? Think about it. We'll come back to that. We're going to talk more about the relationship between free energy and the equilibrium constant here in a moment. Okay, so let's talk a little bit more about enzymes. So this is a word that actually means in yeast, and that's because originally these types of molecules were discovered for the process by which yeast converts sugar into alcohol. Very important reaction. You guys probably know about it. So most enzymes are proteins, but not all. Okay, can anybody think of an example of an enzyme that's not a protein, or at least doesn't use protein in the active site of the enzyme? We talked about it. Anybody? Ribosome. I think I heard it. Yeah, the ribosome, right? So the ribosome makes proteins, but it actually has an active site that's made of RNA, right? So it's not a protein actually. And there's other examples of enzymes that are made out of RNA, but in most cases in cells, enzymes are proteins. They often use metal ions or other kinds of smaller molecules. We call these prosthetic groups, like vitamins, to help out cyscatalysis. And as we said, many inherited genetic disorders result from a defect or sometimes even a total absence of a particular enzyme or sometimes an excessive activity of an enzyme. So the measurement of enzymatic activities in bodily fluids is an important way that we diagnose different kinds of diseases. And furthermore, a lot of drugs that we take as therapeutics can act by altering the activities of enzymes. And finally, of course, as scientists, there are very practical tools that we use in the laboratory. And if you were here when we talked about, I gave my little vignette about biofuels production, you know that we can also, if we understand how they work, we can actually manipulate them and use them for various kinds of industrial applications, like making cellulosic ethanol more efficiently, for example. And I just wanted to show you, give you a little bit of background. Students, I've shown these slides in the past, and students always ask me, do I have to memorize these names and what they did? No, you don't have to do that. I'm just telling you this so that you, just to give you a little bit of the history of the discovery of enzymes. So this guy, Buchner, discovered that yeast extracts could ferment sugar to alcohol, which is this reaction that's shown right here. And what his data showed was that fermentation, this reaction, was promoted by molecules that continued to function when removed from cells. Okay, they continued to function when removed from cells. That means that when he made an extract from yeast, breaking open the cells and taking some of the contents, he could still get this reaction to go. So that really said that there was some property, some types of molecules in these cells that had this fundamental ability to accelerate the rate of this reaction. Then this guy, Sumner, was the first to isolate an enzyme. He isolated an enzyme called jack bean urease that catalyzes this reaction right here. It's very abundant in this type of bean, the jack bean. And what he found when he analyzed the crystals of this sample was that it contained only protein. And so that led him to propose that all enzymes are proteins. And he received the Nobel Prize in 1946 for this discovery. But of course, we now know that most enzymes are proteins, right? There's a few interesting exceptions to that. Most enzymes are proteins. And then finally, Haldane in the 30s postulated that weak chemical interactions between an enzyme and its substrate might be used to catalyze a reaction. And this turns out to be a really important insight. It lies at the heart of, even now, our current understanding of how enzymes actually work. Because most of the time, it's not universally true, but most of the time, enzymes interact with substrate molecules strictly through non-covalent kinds of interactions, right? They have binding sites that allow them to interact with and orient specific kinds of substrates and accelerate the rate at which they are converted into some other compound, some product. And this slide here just shows a surface space-filling model of an enzyme. And I just want you to notice that, very typically what we see, and by the way, these would be structures that are determined using X-ray crystallography, right? X-ray crystallography. So not electron microscopy in this case, but X-ray crystallography to get a very detailed molecular structure of this. And very typically what we see for enzymes is that we see that they often have a pocket, or sometimes more than one, in the structure that has a shape that is nicely designed or nicely organized to interact with a particular kind of substrate, or sometimes more than one substrate, to allow it to bind. Chemistry occurs in what we call the active site on the enzyme, and then the products are released. And this just shows a sort of very simple kind of equation that we can write for an enzyme catalyzed reaction, where we think about enzyme and substrate molecules coming together. They interact to form an enzyme-substrate complex. Chemistry goes on right here, where the substrate is converted to product, and then finally the product is released from the enzyme. Okay? And so there's a couple of really, really important concepts here that I really, really want everyone here to come away understanding. One is that enzymes don't alter the reaction equilibrium. Okay? They don't change that. What they do is they alter the forward and reverse reaction rates. Okay? So they don't change the fundamental reaction equilibrium. Very important concept. And secondly, enzymes themselves remain unchanged after the reaction. Now, sometimes they might change temporarily during the reaction. For example, there's some really cool studies that have been done on some kinds of enzymes whose job is to break down proteins in the cell. And it's been found that these enzymes can actually go through a covalent intermediate. So they actually make a covalent bond with the substrate that helps in the catalytic process, helps convert it to product. But importantly, after the reaction has occurred, that product has been made, the covalent bond is broken, and the enzyme is restored to its original structure and form, so that it's now capable of binding to a new substrate molecule and catalyzing another reaction. Okay, so that's also a really important concept to know about enzymes. And then this just shows some different examples of enzyme-catalyzed rate enhancements. And these are some different examples of enzymes over here and the rates by which they accelerate the reactions that they catalyze. And so you can see that rate accelerations can be absolutely vast, right, by enzymes. So reactions that would take, maybe months or even years if we were waiting for them to occur without an enzyme around, without a catalyst, can happen very quickly if an enzyme is present. Okay? And again, the rates of those reactions can be critical in the cell. And so if we have a situation where somebody has inherited a mutation in a particular enzyme that maybe doesn't completely inactivate the enzyme, but causes it to be defective, causes it to be slower than it should be, that can be sufficient to cause a disease phenotype in a person. And also just to point out that many enzyme names end in ACE. Okay, so if you see a name that ends in ACE, you can be pretty sure that it's some kind of an enzyme. And often what we do is we have terms that will refer. Like these are just telling you specific names of specific kinds of enzymes. But we also sometimes have names that we use to refer to a whole class of enzymes. So maybe you've heard of kinases, for example. Kinases. So these are enzymes that put phosphate groups onto other molecules, typically onto proteins. Okay, kinases. And then the converse of that would be phosphatases. So these would be enzymes whose job is to remove a phosphate from a substrate molecule, such as a protein. And those enzyme families have huge numbers of individual enzymes that all have that same ability to carry out that kind of chemistry. But what makes them distinct from each other is that they are each operating on a different type of substrate. So very typically one kinase can't substitute for another kinase because it would have a different active site that would recognize a different kind of substrate. So it wouldn't work to replace it in a different metabolic pathway. Okay, so let's look a little bit at, this is sort of a comparison of catalyzed versus an uncatalyzed reaction. So this is showing us, again, a plot of the change in free energy over here versus the reaction coordinate over here. And again, we start off in a chemical reaction with substrates in the ground state. They have some value of free energy here. And to get over here to products, they have to go through a transition state, and then they end up over here. And so, as we said, even though this reaction would be a spontaneous reaction, the change in free energy in going from substrate to product is negative. So over time, if we waited long enough, we'd end up with more products than substrates. But it might take a really long time to get there because we have to go through this transition state. And so one of the major ideas about how enzymes actually work is that they lower the energy of the transition state. And so we can think about it like this. So if you think back to that very simple equation that I showed you for an enzyme catalyzed reaction, and we were to map it onto a plot like this, we would start off with enzyme and substrate molecules that are separate. And then as the enzyme comes in and interacts with the substrate, it forms an enzyme-substrate complex. And so there's probably some energetic barrier to that, but it might be fairly small. And there would be a local free energy minimum here for this enzyme-substrate complex. And then because the enzyme active site has sort of favorable interactions with the substrate, and so there's a sort of some favorable energetics going on there. And then often what happens in the active site as well is that it's orienting the substrate so that it's chemically aligned to be converted to product. And so that results in a lowered barrier, a transition state barrier that we can sort of represent like this. So instead of having to get over this high barrier, now the barrier to getting across from substrate to product is much lower. And then we have another sort of local free energy minimum here that corresponds to the enzyme product complex, and then ultimately release of the product. And the enzyme goes away, and of course the enzyme remains unchanged after the reaction, so it can actually cycle back over here, bind to another substrate molecule, and carry out this reaction again, going through this sort of pathway. So this is the idea that if we were to compare the change in free energy of an uncatalyzed reaction, which shows, so we have the transition state barrier shown right here, versus the change in free energy for a catalyzed reaction, getting over the transition state for that reaction, which is shown right here, you can see that this energetic barrier is greatly lowered by having the enzyme present. And so for many kinds of experiments that people have done with different types of enzymes, this seems to be one of the important ways that enzymes function, is they basically allow it to make it energetically easier to get from substrate to product in this way.
Can we say something about coordination in the active site?
Coordination in the active site. We'll talk. We're going to talk more about that on Wednesday. So I'm going to postpone that because I have some slides that will illustrate that a little better. And this is showing you here that the free energy and the equilibrium constant are actually related. Okay, so this is the equation that I showed you before that relates the equilibrium constant to the concentration of products and substrates. And from thermodynamics, the equilibrium constant and the free energy are related by this expression right here. Right? We can either write it with a natural log or we can write it with a base 10 log here if we add this constant. And so if you look at that equation, or even just thinking about it, right, if the equilibrium constant is 1, then the energy that's released is 0. Right? So the concentration of substrates and products are the same at equilibrium. Then the energy released in the reaction is 0. If the equilibrium constant is, let's say it's really big, like 1,000, then then at equilibrium that tells us there's a lot more product than substrate. Right? So this reaction would be spontaneous, and the free energy change would be negative. And if we just plug those numbers into this equation, we get that the free energy released in that reaction is equal to minus 17 kilojoules per mole. And then this just shows you a relationship between the equilibrium constant here and the change in free energy under these standard conditions for different values of the equilibrium constant. And really what I want you to just notice is that when the equilibrium constant is positive, we have a negative change in free energy. So these reactions are spontaneous. They tend to go towards products over time and reach equilibrium with a higher concentration of product than substrate. The converse is true if we have an equilibrium constant less than 1. Right now we have a positive change in free energy. These are not spontaneous reactions. And at equilibrium, we would have higher concentration of substrate relative to product. Right, and so this again just shows you a graphical representation of this, and I would really like for you to be familiar with reaction coordinates drawn like this, with the free energy on the y-axis. And I like to usually throw out a problem or two like this on the exam that asks you to look at a reaction diagram like this and think about whether the information that's plotted is telling you whether or not a reaction is spontaneous, what the change in free energy of the reaction would, whether it would be positive or negative, what you could expect at equilibrium, those kinds of questions. Okay, so be familiar with that, and also think about what we said about the way that enzymes function in terms of lowering the effective energetic barrier of the transition state. And in class on Wednesday, we're going to talk about how enzymes actually do that, because it's really quite amazing. Okay.